So today we're considering applied mechanics, and this is for year 2 for both automotive and heavy equipment engineering. So being the second year means that the foundation science was done, so this builds up. And in this case, we'll focus on the revision. So notice that as we answer the questions, we'll try to be as brief as possible to enjoy the meat of the subject. The first question is talking about, in relation to forces opposing vehicle motion, define the following. Number 1, rolling resistance. So in rolling, it's talking about the rolling motion of a vehicle. Which part of the vehicle rolls is referring to the wheels rolling on the road surface. So that resistance that comes as a result of that rolling action is the one we call rolling resistance. And the major component of that is the friction. So you can even call it the rolling friction, apart from other factors. We also have the air resistance, because as the vehicle is moving, the air is blowing. So it normally moves in the opposite direction to the relative motion of the vehicle. And this one, the main factors that affect it include the area at the front, the frontal area, as well as the shape of the vehicle and the speed at which your vehicle is running. So if the frontal area is so terribly done that it's not able to pierce through the air without problems, then the air resistance increases. You also notice that for racing cars, the shape, they are practically almost spear-shaped for them to move through the air with less resistance. So that is our air resistance there. Then we also have gradient resistance, which is, as the name suggests, the resistance due to that gravitation force coming because of the gradient. So when a vehicle is going uphill, this resistance is going to oppose the motion of your vehicle. If you're going downhill, it's opposite. This becomes not a resisting force, but a force that is going to assist the motion of your vehicle to move forwards, such that if you left your brakes unchecked downhill, the vehicle will just roll down the hill and move without even applying any effort to it. So that's how the gradient behaves. So here's a question that we're going to apply. Says, we have a truck of mass 2.7 ton and driven downhill at an incline of 1 in 120 from rest at an acceleration of 3.2 meters per second squared. Their resistance is 222 newtons and rolling resistance 92 newtons per ton. If the incline of the truck is 14 meters, determine the tractive effort and the work done, just those two. So traditionally, whenever we're dealing with analytical questions, we say, start with arranging information provided. So we pick up the data. The first thing we have is the mass. Now, the SI unit for mass is not tonnage, no, it's the kg. So to convert from tons to kg, we multiply by 1000. So this is where this is coming from. Then one thing you'll notice is that when we say an incline, we normally compare two things. Let me just quickly make an illustration. We normally compare just two things here. For example, oh my God, maybe not this one. Let me undo this one. Pick up a better pen. Oh, yes. So we normally say, for instance, this is my path. That's the height. And of course, this is the horizontal side. Suppose this is it. Now, for every 1 unit ascension, or for every 1 unit you go up vertically, you've moved along your path by 120 units. It could be that you've moved 1 meter up, then along the path you've moved 120 meters. So that's the meaning of 1 in 20. Now, mathematically, we know that when we go back to trigonometry, this angle here, given this information, we already have the opposite, and this is the hypotenuse. So the ratio between this and that is the one we call sine theta. So that's our sine theta. Hence, we've written here sine theta is equal to 1 over 120. Moving on, we also have the acceleration. This vehicle is also accelerating at a rate of 3.2 meters per second squared. Then we have this constant number here. We've been given 222 newtons as the air resistance. Length of the track, we will call it as D. It's a displacement. We can also consider it to be S. It's 14 meters. Then the rolling resistance has been provided as 92 newtons per ton. When we get to the working, we're going to interpret this. When you say 92 newtons per ton, you're saying that if this track was 1 ton, then the rolling resistance was just going to be 92 newtons, which means that to cancel it out, we'll multiply this 92 newtons per ton by the tonnage of the track. Then we'll be able to realize how much rolling resistance we're dealing with for this particular track. Now, we need to find the tractive effort. So what we are going to do is to calculate each of the resistances that we're having. Now, what we are calling gradient resistance is no longer gradient resistance, but because that's what we designate it, we'll leave it like that. But here, it's going downhill. So realize, we'll remember that and ensure that we take care of that in our calculation. So gradient resistance is simple. It's simply mg sine theta. Now, like I've said, because we said resistance, but it has refused that it's no longer resistance. That's why we've given it a negative. So that when we're summing up the resistances, this one will be subtracted because it's no longer resisting, because this vehicle is going downhill. Let me come again on that. We're saying that the gradient resistance in this case is behaving in a different way. It's no longer resisting because our track is not going against resistance, or rather against gradient. It's going downhill. It's going down the slope. So this component of the force is actually going to assist the vehicle motion. Therefore, it's not a resistance. That's why we've given it that negative. The other resistances we want because we are going to sum them up together. So with that in mind, the idea is this is just mg sine theta. Mass is 2,700, g 9.81. Then sine theta is 1 over 120. Again, when you look at 1 over 120, it represents the whole unit as sine theta. If you want to substitute for theta, it means you have to calculate for theta. You say theta is equal to sine inverse of 1 over 120. Get the angle and substitute there. Then you're going to write it like this even here. But what we have done here is that we've substituted for the whole sine theta as one complete unit like that. We're not substituting for theta. We're substituting for sine theta, the value. So that's why in place of sine theta, we've put 1 over 120. Meaning our gradient resistance, therefore, the number is 220.725. Rolling resistance. The rolling resistance that we've been given is 92 newtons per ton. Now, one thing you're going to notice is that this one here, the ton, will cancel because it's 2.7 tons. And you remain with the newtons. So 92 times 2.7, hence you have your total rolling resistance, which in this case now is actually 248.4 newtons. Next, we've also, one thing I think it didn't include here is that in fact, it will come later. We also have the air resistance, which is actually 222 newtons. So that one, there's no need to calculate it because they've already given us. So it actually makes our move even faster. Now, this track is going to accelerate. So we have an accelerating force, which is F is equal to ma. So our m is 2,700, acceleration 3.2. So our accelerating force, therefore, is 8,640 newtons. In addition to these resistances, this is what the tractive effort should also overcome. Suppose you just manage to overcome these, it means your vehicle is able to move at a constant velocity, but it may not accelerate until you put this extra force for it to accelerate at the rate that we were given, the 3.2 meters per second. Air resistance, thanks, I think I didn't know that I already taken it up. Our air resistance was already provided as 222 newtons, so this one is straightforward. There is no need to calculate. It's already been provided. Now that we have all these, let's find the tractive effort. Now, one thing we have is that we have all these to be added together: rolling resistance, gradient resistance, accelerating force, and the air resistance. So we just sum them up. So yeah, this is supposed to be plus as it has been given in the formula. So we just replace rolling resistance was 248.4. We said that this gradient is assisting because it's going downhill. That's why we decided to actually subtract, because it's no longer a resisting force. So minus 220.725, the accelerating force 8,640, air resistance is 222 newtons. From there, our tractive effort is 8,889.675 newtons. This is the effort that the engine should propel for this vehicle to move, overcome the resistances, and also accelerate at 3.2 meters per second squared. Work done is normally force times distance. In this case, the force is the tractive effort. The distance was provided already, d. So we just go ahead and say E, which is the tractive effort, times the d. So the tractive effort is 8,889.675 times 14. Hence we have 124,455.45 joules. Question number 2. Definitions as usual: potential energy. Of course, this one is sometimes we also call it as gravitational potential energy. The energy that a body will have because of its height above a surface or above a datum or above a reference point. That is our potential energy. Kinetic energy is that kind of energy possessed by a body because of its motion, or by virtue of its motion, or due to its motion. Principle of conservation of energy states that You can neither destroy nor create energy, but it can only be transformed from one form to another. So you have heat energy being transformed to work done, heat energy being transformed to perhaps sound, and so forth. So you can neither create nor destroy, but can only transform energy from one form to another. With that principle in mind, we have this question. A hammer of mass 0.8 tons falls through a height of 2.8 meters from rest onto a pile of mass 320 kg. The hammer does not rebound on impact and drives the pile a vertical distance of 100 millimeters into the ground. Calculate the striking velocity of the hammer, common velocity of the hammer and the pile, accelerating average resisting force of the ground. Information. So what we are seeing is that here is a hammer. This could even be a forged hammer, held at a height of 2.8 meters from where the pile is resting. Then it is dropped, allowed to fall through that height. When it hits onto the pile of 320 kg, this combination of the hammer and the pile penetrate the ground by this much, 400 millimeters. So let's get started. First, what is the mass of the hammer? It's 0.8 tons. And one thing we said about tonnage is that 1 ton represents 1,000 kg. So 0.8 ton multiplied by 1,000, that's how come we have that number there, which is 800 kg. Then we also have the height through which is going to fall, which is 2.8 meters. Mass of the pile, 320 kg. Distance into the ground, this is the distance, the whole combination of the pile and the hammer penetrating into the ground is 400 millimeters. But we're using SI unit, so we have to convert to the normal SI unit. We divide that by 1,000. So it is 0.4. Now, striking velocity of the hammer, we go to the translation, conversion of motion energy rather from potential energy to kinetic energy. That's what will happen, that when the hammer falls, the potential energy it had when it was held at 2.8 meters is converted to the kinetic energy. So you see some velocity of the hammer as it now strikes onto the pile. So what do we do? The formula for potential energy is mgh. Formula for kinetic energy is half mv squared. So here you can see that m will cancel. Then you make v the subject. And that's why you now have square root of 2gh. So we can substitute. 2g is 9.81. The height through which the hammer should fall is 2.8 meters. So square root of that, you end up with 7.412 meters per second. That is the height, that is the velocity with which the 800 kg hammer is going to hit or strike the pile. Then what is the common velocity of the hammer and the pile? Now here we have a problem. This hammer came with this velocity. It dropped onto the pile. We don't expect this velocity to be maintained after striking the pile because it's going to be met with some resistance. So what do? We are going to introduce collisions. We're going to introduce the principle of conservation of momentum, where we say that momentum before collision is supposed to be equal to the momentum after the collision has taken place. So here, one thing is that the question was saying the common velocity of the hammer and the pile. meaning that we're dealing with an inelastic collision where the two bodies stick together and move as a unit in one direction. And in this case, it was movement into the ground. So we have some of initial momentum, which is m1u1 plus m2u2 is equal to m1 plus m2v. 1 is the hammer. Body number 2 is the pile. So mass of number 1, which is that of the hammer, by the initial velocity of the same number 1, the hammer, plus mass of number 2, which is the pile, times velocity 2, initial velocity of this number 2, which is a pile. Then we add them here. This v is the one we want, which is the common velocity. So we need to find what it is by substituting. So in our substitution, we've said mass number 1 is 800 kg. With what velocity did it hit the ground? Did it hit the pile? It's this one we found here, 7.412, plus mass number 2 is the pile, which is 120 kg. At what velocity was it moving? It was at rest. The pile was not in motion. So that's why for the U2, we're saying it's 0. Equals, then we add the two masses, 800 plus 320 kg. Then we make V the subject. So after all this workout, the velocity drops down to 5.294 meters per second. So here, you remember the principle of momentum dealing with inelastic collisions. That's the principle we've used here, and that's our answer. Now, the average resisting force of the ground. Here, we introduce the same principle of conservation of energy we referred to earlier. The work that is going to be done by the ground in resisting that motion of the pile and hammer entering the ground should be equal to the loss of kinetic energy and the combined potential energy loss. Remembering that this is actually going to penetrate the ground by some distance, so meaning that there's also going to be some loss in potential energy. Then one other thing is that when penetrating the ground, it is a combined mass of both the hammer and the pile that is actually at play. So we have to ensure that we use that velocity, that kinetic energy with which this unit penetrates the ground. So what are we saying? The work done by the ground is force times distance, but I want to be very specific. What I'm calling H1 here is the height through which, or rather the depth through which both the pile, a combination of the hammer and the pile, penetrate into the ground. That's the one I've called H1. That's the one I've referred to as H1. Then we're saying that there's going to be some kinetic energy of this combination of the hammer and the pile. So we're saying half mv squared. That kinetic energy should be overcome. So a combination, we add the two masses this time. Mass of the hammer plus mass of the pile times v squared, and there's half there. Then plus, here it's mass of the hammer plus mass of the pile, GH. It's supposed to have G there, times 9.81. Of course, I will include it. Let me even put it right there, and then it will deal with the rest. So that's supposed to be G. Again, here you have it. We're saying the potential energy is Here it's F, that force, the resisting force, times 0.4, because here that is work, the formula for work done, is equal to half. Our M is 800 plus 320 times the V squared, which is actually 5.294 squared. Then here we said that there is 320 plus 800 multiplied by 0.4 multiplied by 0.4. But one thing I mentioned is that we also need to include, let me just bring up a pen here, we add it. Yeah, it's here. We also need to include times the gravity, which is 9.81, times our gravity, which is 9.81. 9.81. That's how we complete it. So what are we saying? Here we're saying that you add, first of all, half multiplied by this combination, which is actually 800 plus the 320. Then multiply it by 5.294 squared. Now this one, we're adding it to this. We're saying plus. This is like 1,120. When you add 320 plus 800, so 1,120, then you multiply that by 0.4. Now this 0.4 is the height. And since it's potential energy, we include 9.81. With that, we get one side, the value that is needed. But then we are making F the subject. So then the answer, let me just remove this. So here we are making F the subject, and hence our answer becomes, just a minute again, okay, 40,357. But because of this small correction, you'll find that our answer is actually 50. It's supposed to be 50,224. So 50.2 kilonewtons. Kilonewtons. That is our resistance the ground is going to offer as a force. Let me remove that again. And also remove this. Right, let's pick up the next one. Now, question number 3 is talking about what is a velocity diagram. When you talk about a velocity diagram, it is where you look at, it could be a link mechanism or some other mechanism where you represent the velocities graphically. Bring them together into a graph. Then what you've come up with is a velocity diagram representing various points. So that is a graphical presentation used to show the magnitude, direction of those velocities that you're dealing with at given points. That is a velocity diagram. Instantaneous center, here we talk about a point on a mechanism where the body is rotating or a specific instant or at a particular time. So that becomes your center at that given point, and it keeps changing depending on the mechanism. So part B, we have a slider crank mechanism as shown in this diagram. Crank OA rotating at 70 revolves per second clockwise. The length of crank OA is 200 millimeters. Length of connecting rod 700 millimeters. Piston B slides back and forth along the horizontal line OB. So graphically or analytically, for the position shown, determine angular velocity of crank OA, velocity of A, velocity of piston B, and angular velocity of cone rod AB. So with this information, we can now come up with the data. First, the length of the crank, which is R, like R OA is 200 millimeters, which is 0.3. Next, we also have the length of AB, which is R for AB. This is the cone rod, is 700 millimeters, but we convert it to meters, becomes 0.7. Now, the first question is asking for the angular velocity of crank OA. Here, we just use 2 pi n because the rotational speed in revolutions per second. So 2 pi n. So 2 pi times the 7. So in the end, it's like 140 pi or 439.823 rads per second. That is our angular velocity. Velocity of point A. So now velocity of point A is basically trying to say, we just do the conversion. V equals omega r. So V at A is the angular velocity of OA times the radius. In this case, we already have 439.823 times our radius, which is 0.3. That's where we end up with 131.95 meters per second. Now here, remember to differentiate. When it's talking about angular velocity, it specifies. For linear velocity, because this is the main subject, even the velocity diagram we're drawing is representing the linear ones. That's why it remains, it just says velocity. And we have to pick that's the one being referred to. What about velocity of B? So velocity of B, in using the graphical method, the first thing you do is to copy the diagram. Then for members OA and AB, you draw perpendicular lines because that is how the velocity, the linear velocity behaves. Then you combine that into a velocity diagram. So in my case, after doing that, you notice that the scale that I used now after that was that 5 centimeters was representing 131.947 meters per second. We're now converting into a velocity diagram where you put together those perpendicular lines and the sliding motion of the crank. So when in measuring, it gave 5.3. So with that, we go back to our scale. This one we have here. 5 centimeters represents 131.947. What about 5.3? So we do the cross multiplying, and our answer becomes 139.47. This is the linear velocity of the piston. That is the velocity of piston B, 139.87. So this is just a typo error, 139.87, not the one we've put there. 139.87. Then the other part was asking for the angular velocity of cone rod AB. So the angular velocity of cone rod AB, you look at the same velocity diagram that you cropped up together, and that's where you find that it's 3.2 centimeters. That's what you've been provided with. That's what comes from there when you measure. So here, I decided to use the other scale, which refers directly to the angular velocity. So the 5 centimeters initially represented 140 rads per second. So in the end, what about the one that we are having? So we just say this is X, then we cross multiply, and the result is 281.487. That is the angular velocity in rads per second. So the secret when you're dealing with this one is just to make sure that you have the information right, because this diagram, the movement of OA, we're told it's clockwise. So here for OA, that movement, the linear movement, will be at 90 degrees to OA. Just like AB, the movement of AB will also be at 90 degrees. So here, I can say you plot up that perpendicular line I was talking about. Here also, this perpendicular line. Doing this is simple because you just use your set squares and you're good to go. Then after that, the very first one to draw, the one that you have to start with when you're now coming up with your velocity diagram, is this one whose value has been provided, OA. So here is where I use the scale of 5 centimeters to represent 131 point that meters per second. And respecting this direction, remembering that we're going clockwise. So here we transfer it and we measure the 5 centimeters from O here up to A there. Now, that is a very special letter. Okay. Right, OA. Then from there, the next one that you bring up is this one here. This is representing AB. And since we are moving clockwise, it means it's moving in that direction. So we lift this. In your case, with the help of your set squares, with the help of your instruments, you transfer this there. You just draw it randomly like that. And lastly, you bring OB, the movement of the slider, because this is moving in a straight line. It will be transferred also there. Blindly, because we don't know where they will meet. So they meet at point B. So when the question is saying, find the angular velocity, rather find the velocity of piston B, you measure this OB, that one. When you measure, in my case, this is the one that gave me 5.3 centimeters. Then I refer back to the original scale that I had where I said 5 centimeters is representing the velocity of OA, which was 131. And then we calculate backwards to find what this distance I've measured is representing. So it's like we're now interpreting the velocity from the velocity diagram that we've drawn, because this is our velocity diagram. So in the graphical method, things are as simple as that, as long as you ensure that you've carried your instruments, then all will be just. The analytical method is also there. There are several approaches we do to that, and we can equally explore that at another time. For today, we'll cut here so that the other part, we'll finish up the remaining questions. And please feel free to point out where you notice an item requiring some clarification.